Hello, everybody. It's nice to see many people's names that I recognize. I hope there are people there behind the names. Wish I was with you. But anyway, we will cope and get through this challenge. If life had no challenges, it wouldn't be interesting. Okay, so let's see. So let me pick up from last time. First, I should share my screen. How about that? Are you seeing my share?
Yes, we are.
Seeing it? All right, now let me pull up the chat window so I can see out of the, while I'm talking, if people have a chat. So I do want to encourage you to type questions while I'm talking. That way you don't have to remember. I think that's one of the advantages of this form of communication, is that you can put out your question and we can deal with it at any time. So I think we're all learning how to use this technology. So just to remind you, my main topic is machine learning and prediction of sequential images. And I tried to combine some general considerations with the particular application that I looked at. My colleague Eslam Hussein is here with me, and he may add some comments in the chat window or while I'm talking. So let me go back over starting from some slide here. So I'll start from here. Let's see. I'll go back over some of these quickly and maybe add a few points. So mathematicians will appreciate that machine learning is really the process of constructing a function from data. It's constructing a function of vectors, and it's constructed using one data set and applied to other data sets. You can have different kinds of functions, discrete or continuous. In our case, we created a continuous function. So the vectors can be multidimensional, very high dimensional vectors. In our case, they're not quite so high dimensional, but you can have, in the case of image prediction with convolutional neural networks, you have input vectors that have thousands or 10,000s, possibly up to 1 million dimensions. This is kind of something new. Of course, in classical mathematics, you don't think of functions on that many dimensions, but that's what computation brings into the mix. Okay, so machine learning can be used for prediction and classification. So in our case, we used machine learning for prediction of images, and these images represented a groundwater level. The important sets involved are the training set and the testing set. Now, last time, someone mentioned the verification set, and from that question, I can tell that people are interested in neural networks, because that's a neural network concept in the modern machine learning techniques, such as support vector regression or regression or random forest. There is no verification set. So for our purposes, there are two important sets. There's the training set, which you use to construct the function, and then the testing set, which you use to make sure that the function is doing what you want it to do. And there's a question: how do you divide between testing and training? Because both are important. If you have a limited set of data, somehow you will have to use some for the testing and some for the training. And I think that what people do is they basically just try something. Usually most of the data goes for training and then part of it for testing. But I'm not aware of any systematic study of what is the best way to divide data between training and testing. I think that might be an interesting research topic for mathematicians. So much of this field is not rigorous. It's done just because it works. So there's a lot of work to be done to try to improve the method. Okay. So I talked about 3 tiers of machine learning. There's the classical, which is regression, which comes from statistics. I think I mentioned that statistics and machine learning overlap very much. Sometimes there's a competition between two. There are articles by statisticians that criticize machine learning. And I think machine learning, I think people are still trying to respond to those criticisms. Because certainly statistics is a much more well-developed field, although it's not that old, maybe 100 years old. But hopefully within a few decades, machine learning will be as well-developed as statistics. Okay, sorry. Okay. All right, yes, okay. So, all right, so I mentioned the classical. So these are some important algorithms in classical machine learning. And I do encourage some of you computer scientists to look at this type of machine learning and not just jump straight to neural networks. Someone last time mentioned that they were looking at maze images for, I believe it was for disease. So you take several images of maze and you try to train the machine learning to recognize whether the maze has disease or not. Now, in such applications, I think there's no question that you need neural networks because of the complexity of the input data. But in many cases, especially with smaller data sets, you might want to go to the modern methods and not directly to neural networks. So this is a choice that you should consider carefully when you're doing machine learning. Don't just immediately assume that you're going to use a neural network. You should be aware of the options. You really want to choose the very best tool for your job. All right, so here I mentioned deep learning. So unfortunately in this talk, I'm not talking explicitly about machine learning, about deep learning. I'm sure that people have questions. If people have questions, we can talk about them. But our data set was not large enough. So these are the stages in our process. So I mentioned this, you start with an image data set, you do some pre-processing, very, very important. This is really where the human intelligence comes in, where you do feature selection and engineering. And this is an extremely key part of the process. And this really can make or break your process. And this is where you do need to know and understand what makes your data work and what's important about your data. Right? Then you split your data into, you split your data into training and testing. Then you use the training data to train your model. Here we train several models. These are trained independently. And then the trained models are evaluated using the testing set. And I mentioned my 6 commands of machine learning. And I think those are on the next slide. Understand your data, pre-process your data intelligently, maintain data integrity, compare with a simple baseline model, use an algorithm appropriate for the amount of data, and determine the significance of the results. So, all right, so these different commands affect different parts of the process. And so I said to understand your data, the key idea here is correlation. You want to put together. I think the mathematicians will understand what correlated means. If you have 2 Gaussians, they can be independent. Or if the 2 Gaussians are combinations of the same Gaussians, they may be correlated. You want to put the correlated data together because the correlated data in some sense is redundant. So when you're doing data reduction, the whole idea of machine learning is to take a lot of data and reduce it down to a small amount of significant, important data. So you want to group together the correlated data. This is why in convolutional neural networks, so I can say that machine learning can be thought of as a process of data reduction. And you take a lot of correlated data and then you condense or distill to what's important. Okay, so I can do, for example, this is actually the philosophy behind convolutional neural networks. Now, what is a convolutional neural network? Well, you have an input data, which is an image. So this is one case where you have a huge vector. You have, your input data is a maybe 1,000 by 1,000 pixel image. Sorry. Okay. So the input image will have pixels. So I'm going to divide this into pixels. Now, if you have a picture, say, of a cloud or of an ocean, so let's say there's a picture of an ocean, then you've got ocean down here, and then you've got your sun up here, your bright sun up here, and you've got a cloud over here. Let's make a nice gray cloud. Here's a nice gray cloud over here. Okay. Okay. And so maybe you have birds or something, very nice seashore picture, and you've got the seashore over here. Okay. Right. So here's your picture. Now, notice this pixel here. This pixel here is very closely related to the neighboring pixels, right? So these pixels are correlated. So your neighboring pixels are correlated. So what does a convolutional neural network do? Well, what it does is it takes a window or a patch, maybe a 3 by 3 patch of the image, and it will take this and it will take some kind of average. Now, why does it do that? Because this data is highly correlated, right? You don't need the individual information from all of those pixels. Instead, you can use the averaged. You can use the averaged data, but this window, of course, is not enough. So you take this. So you take this window, and then you slide the window along. Okay. So you get and if you're a mathematician, you'll recognize that this is actually what you do in convolution. That you're sliding a function across a function. So I take this window, I slide it along the image. So I get lots and lots of averages. And then from those averages, you select the important ones. You may select the largest, you may do something else like that, but you'd select some of them because you don't need all of them. Okay. So you may, if you basically take one for each average, you can reduce your data by maybe by a factor of 9. Okay. So if you select 1 from 9, select one value from 9 averages, that means you've reduced your data by 9. Okay. All right. So the idea about machine learning is that you do, the ideas about convolutional neural network is that you have layers, and each layer reduces the data by some factor. Okay. And then the law of exponents kicks in because you can see that very, very quickly. If I, for instance, if at each stage I reduce my data by a factor of 2, then after 10 layers, I've reduced my data by a factor of 2 to the 10th or 1,000. Okay, so this is the power of layers, layers that successively reduce the size of the data. Now, this is an oversimplification. There's more than one type of layer, but some layers do have this function of taking your data and reducing the amount by combining correlated data. Now, there can be long-range correlations or short-range correlations. In this case, the correlations are short-range, but sometimes you may have correlations over a large region. For instance, this blue shows very long-range correlations, or you might actually have correlations from different parts of the picture. So this is why where the complication of neural networks comes in. Neural networks try to take a combination of local features and global features and put them together to make some choice about the image. For instance, you might have a machine learning algorithm to try to tell which beast this is. Is it from France? Is it the Lagos Beach? Is it somewhere else? It's in South America. So you can see that there'll be you'd have to look at many features to see the color of the water, the shape of the clouds, the configuration of the beach, and so on. This would be some very complicated combination of local and global features. So neural networks does all of this, and it does it invisibly. You don't really know what it's doing. In this sense, it's like human intelligence. The human intelligence is quite incredible. A human can look at a picture and recognize where the picture is coming from. And there's some kind of very complicated process that's not well understood. And the idea is that perhaps this process of machine learning is imitating the process of human cognition. So that's all right. So that's my digression about correlation, a very key idea in machine learning. Now, in our case, we have data. We had global data. You can recognize this as the globe. These are land areas, and the more red color means higher groundwater level. Okay. We had monthly images. We only selected a small region. You can see the region of South Africa, and the images, I think I said already, the images were taken monthly, and we wanted to use a set of previous images to predict the next month's groundwater level. I did mention last time that this data has certain important characteristics. Number one, the groundwater level this month will depend strongly on the groundwater level in the previous month. Because the groundwater does not vanish instantly. The groundwater is residual. It evaporates slowly, or it moves slowly. So there is some dependence on the previous month. Groundwater is also seasonal because weather is seasonal. So we have both what you could call Markov and seasonal dependence of data. And we want to be able to catch both effects in our machine learning prediction, both the seasonal and the previous month influence. All right. So some ideas, some things that you have to know about your data. You want to remove the background data. You also want to do data imputation. Some of the images were missing. Okay. So I mentioned that last time, data imputation, there are various techniques for this. And let me amplify today a little bit about data imputation. So this is kind of a heuristic idea of how to do data imputation. I'll try to write more neatly so you can see what I'm saying. All right, so what is data imputation in this case? I'm looking at images. Okay, so if I have a sequence of images, okay, and maybe one is missing. Maybe this one is missing. all right, very good. Let's see. All right, so what can we do to fill this gap? Because we need to, if we're going to predict sequentially, we're going to have to fill this gap. So we can initially fill this gap with the previous image. All right, so let me just be a little more clear. Maybe this could be from April, this is from May, June is missing, July is there, August is there. So initially we can fill this from the May image, right? So we take this image here and we duplicate it here. So this is basically a fake image. Okay. Now this completes my data set, but it's not a very good completion. Okay. So I can call this my initial completed data set. Now, what I can use is I can actually, I can use a bootstrap method to impute the data. Okay, what do I mean by bootstrap? I use this initial, I use the initial completed data set, use initial data set to construct, to train a model. I could take any model, okay, or so I can use this to train a model. Okay. Now this model is a predictive model. So this model will predict images. Okay. All right. Now I've constructed this model based on this data set that had missing data. But now I have a predicted model. I can use this predictive model to fill in the missing images. Okay. Right. So because now I have a way to decide what images should go there. So I should be able to use that to predict these missing places. Okay. So that's what I do now. Now instead of this same sequence of original images, I'll use a model to fill this place. And this model will depend not just on the previous image, but it will depend on several previous images. Okay. All right. So that will give me a better estimate of missing data. Okay. Now, once I have this better estimate, this is my second iteration. Now I can use this iterated data to retrain. Okay. Those of you mathematicians who do fixed point, you know this. This is what you do. You iterate to convergence. Okay, so I'm using this. I'm getting a better estimate this time, and then I can redo. And then you could repeat until no more convergence. Repeat until no more improvement. Okay. So this is some idea of how you can use this kind of mathematical idea of iteration to improve your data imputation. So we did not actually use that in this paper, but we did explore this technique, and it actually did improve the performance of the predictor. Okay, so, all right, so when we identified features, we converted the color image to grayscale, because all we care about is, for each pixel, we only care about a single number. Okay, I see a question here. It says, is it reliable to predict the missing value with the field mean? Uh, so, uh, so you, so I'm not quite sure what is meant by the field mean. It may, I think that in this case, I'm not sure if by field mean that means the image, the average over the entire image. But taking a single mean is probably not going to be a very good, a good way to impute missing values. It really depends on the particular application that you have. Okay. If I had a single missing pixel, then you might replace that pixel with the average of neighboring pixels. But in this case, I'm not sure. You might try to take some average of two neighboring images, the image before any image after. But I think that some iterative method like this should be able to perform better because you're using a predictor that is proven to improve the missing data. I thank you for the question. So, all right, so so let's go back to this, what we're talking about. I'm taking my original image and I convert the color information into a single scale from 0 to 255, right? And then to predict 1 pixel of my 13th image, I choose the 12 previous images. Now, why do I choose 12? Right, this comes from knowing my data. I know that my data has a periodicity according with the weather. So I expect the 12-month previous image to have some influence on the image of this month. I expect that January last year will give me a good idea about January this year. So I want to include 12 months back. I also know that December last year will be good for January this year, so I certainly want to include that. And the others I include because there may be some influence. So of these, we have to identify important features. So I talked about this. There's several methods for feature selection. Now, my colleague Eslam, he may, if you're there, please, I don't remember what package you used to do this. I think so you can type that into the window, but there's a package in, so I just tell you that the package that we used is called a scikit-learn. This is in Python. Okay, and we use this package to do the machine learning, and you'll see that in the code as we look at the code later on. So we identified the important features. Not surprisingly, the most important feature was 12 months previous. Next was the previous month. But it's kind of somewhat surprising that 11 months previous was also a very good feature, not much worse than the previous month. But I think that the 11th month previous does not add much new information to the 12 months previous, and we'll see that in the subsequent analysis. We also created a global feature using Gaussian mixture model. I mentioned how we did this. Here you can see in the original image, there are clusters of pixels where the image is bright. So this is the original transformed image. Here you can see Madagascar. Unfortunately, I don't think Nigeria is here. Nigeria is up. The image is upside down. Sorry, this is South Africa over here. Nigeria would be up here somewhere. So I'm sorry that this, if I could rotate this, if you looked at this upside down, you would recognize that this is the bottom part of Africa. But you have this cluster of images where the value is bright. So you want to get some feature that will capture the cluster and not just the individual pixels. So one way to do this is to fit a Gaussian distribution to the points. Now these would also be outliers. The Gaussian distribution is centered down here. You know, Gaussian distributions have mean and variance. So this will have an X mean or Y mean, and it will have a 2x2 covariance matrix. So, okay, so the 2x2 covariance matrix will have two principal eigenvectors, and so we use the location of the mean and the two eigenvalues as features. We didn't want to use the entire covariance matrix because that's just more, that's a lot of information. You don't want to give too much information to your algorithm because then the algorithm has to sort it out. And we'll see shortly that if you do give too much to your, if you do give too much information to your algorithm, the algorithm starts performing worse because you confuse it. Just like with a person, if you give a person too much information, they'll be less likely to be able to make a decision. Okay, you can see in your chat window that Eslam has given you the scikit-learn functions that you can use to find importance of features. That's not in the code that we show later on, so I wanted to mention that. All right, maintain data integrity. I talked about that last time. Okay, compare with a simple baseline. Okay, all right. So we used multivariate linear regression, which is a statistical method. Okay, we also used two other baselines, which is the previous month and the 12 months previous. So those are very, very simple baselines, which we should be able to improve on. Okay, so I said several times about be careful about using deep learning. Don't jump to it too quickly. So I can pass by this one. Okay, and we have two measures of error: the absolute error and the root mean squared error. What's the difference between mean absolute error and root mean squared error? Let's see. Again, this is something that we can, that I think mathematicians will appreciate. Okay. All right. So what's the difference? What are the relative advantages of these two? So in my slide, I show the formulas for those, but here let me give some idea of if we have some distribution. Okay, so let's just have a single variable. And we have some true value. So here's the true value of some parameter. Okay, and then we have a cloud of data points. Let's use a different color here. I can use this. I have a cloud of data points. Okay. Now the mean absolute error, what you're going to do is you can see your errors are. You have several errors here. Each one of these points has an error. This one has an error. This one has an error. This point has an error. All these points have errors. Right. Now the mean absolute error is just the average of these lengths. Right? This has a length. This has a length. Now you don't want to average the signed lengths because then you'll get 0. If this is at the mean, then the average of the signed lengths will be 0. So it's just going to be the average of the error so I can just say individual point error lengths. Okay. So this seems like a good method. If you want to find basically how far away your next data is going to be, and you take the mean absolute error, that should give you some good idea of how far away typical data point is from your actual value. Now the root mean squared error is you take instead of averaging the values, you average the squares. Of the lengths. Okay. Now, this is the same thing as standard deviation. Okay. And standard deviation, of course, is what you use in statistics. Okay. So standard deviation has a lot of very, very nice theoretical properties. So for theoretical reasons, mathematicians often use this root mean squared error because of the nice properties of variance. However, the problem with root mean squared error is root mean squared error is more sensitive to outliers. And you can see this if I have some data here. And here's my true value, and then I have some cluster of data points here close by. I have a lot of data points here, and then I have one outlier out here. Okay. So this has a very large error. Maybe this is my 47th data point, so I'll call this E47. Now, if I take the mean absolute error, I'm going to take the sum of the absolute values of all my errors like this. I don't know if maybe I have 100 data points. And then I would have to divide by 100. Okay. Now, the root mean squared error, I take the sum of, instead of this, I take the error squared. And then I'll take this and divide by 100, and then I take the square root. Now look, if this E47, suppose this distance is 100, right? Here, if I have 100, then this 100 will just get averaged in. It will just have an effect of 1, right? Because I have 100 here and 100 here. But if I have 100 and I put it in here, that 100 becomes 10,000. Okay, so this 100 has a huge effect on the RMSE, much larger than it does on the MAE. Okay. So that's certainly a drawback with the root mean squared error. So that's good that you can, by comparing the mean absolute error and root mean squared error, this gives you information about outliers. Okay. So in other words, if the mean average error is small and the RMSE is large, that means that you have outliers. Okay. So that's one reason why it's good to have more than one method, more than one measure of error. So all right, now there's other ways of showing significance. We should actually show these others later on, so I want to spend some time. It is very important to represent your data. That's a very, very key part. You should put a lot of thought into how you represent your results. Now, this can actually make or break whether or not your paper gets published, because if you just present your results as a table, the reviewer looks at it and says, what do these numbers mean? So you have to make sure that your numbers tell a story. All right, so here's our story. So let me take a little more time to explain what this is saying. All right, so I mentioned that we used several algorithms. And these algorithms were extreme gradient boosting, random forest, linear regression, multi-layer perceptron, and so on. So you can see the different colors here represent the different methods. Let's see, where's our baseline? Well, the linear regression is our baseline. All right, now these down here represent different prediction schemes. They represent different input vectors. I have it several slides up. the A, B, C, D, E, F, G, these represent different sets of previous months that are used in the prediction. So let me scroll back up quickly and see if I can find that. Oh, sorry, you have to go up this way. Okay. Too slow. Let me see if I can. All right, let me just go back. Is it gonna let me go back? I want to get out. All right, so here. So let me find it. It's back up here. All right. So A, for instance, is used the previous month, 12 months previous, and the previous month. B is using 12 months previous, previous month, and then 11 months previous, and so on. So we have different combinations. Looking at these features' importance, we selected these sets of previous months for the prediction. Okay, so I'll start the slide here. I'll start the show here. All right. So that's what A, B, C, D, E, F, G means. This means looking at different combinations of previous months. All right. Then you have A plus IJ, B plus IJ. Here, besides this previous month information, we added location information. We told the machine we told the machine where the pixel was. So we added these two pieces of information to our input vector. In this, so that's this group of predictors here. Include both the month information and the location information. This group includes the month information, location information, and timestamp. There are 12 different timestamps. 0 is January, 1 is February, 2 is March, all the way up to 11 is December. So this is helpful because this gives the algorithm some idea about the seasonality. It tells you when in the year the picture was taken. All right, now this last one is it adds another part which says the square root. Okay, you see my colleague. He put the month predictors in the chat window, so you can see those for your reference. All right, so here we added square root feature. Now, why would you want to take the square root of your data? Well, taking the square root of the data is another way of reducing your outliers. Right? If I take the square root of my data, then this outlier distance is going to be reduced. This large outlier, this 100, will be reduced down to 10. So this is another technique for reducing the spread of your data. In our case, a lot of the groundwater data, you have very low groundwater values, and a few very high values. So you would like to compress your scale so the low and the high are, so that the low and the high are not so different. If I have some kind of distribution, in fact, this is a general consideration in information theory. So if my distribution of pixels looks like this, if my distribution of pixels it looks something like this, that I have many low values and few high values like this. Okay, so that means in some sense that you're getting more information down here than up here. What you want to do is you want to whiten and you want to whiten the data and make it more uniform. Okay, I said that wrong. If I have a pixel down here, that gives me very little information because these pixels, there's a lot of pixels that have similar pixel values down here. There's only a few pixels that have pixel values up here. So in some sense, this is giving you more information than down here. What you'd like to do is make the distribution more uniform. Okay, so this is pixel value. Now, if I transform this data, and instead of taking pixel value, I take the square root of the pixel value. All right. Then, like I said, if this is 100, it gets compressed down to 10. And this curve becomes much more flat. It's not going to be completely flat, but it's going to be much more flat. So your data is more uniform and thus well behaved, and the outliers have less effect. I don't know if you do this in Nigeria, but in US, I don't know if you've heard of this expression. You grade on the curve. Sometimes you give an exam and most of your students are failing down here. And you have a few students up here who are doing well. So this is up 100. Then this maybe you have 50 down here. Okay. So you want to grade the students so that not everybody fails the class, because you don't want to teach everybody the next year. So what you do is you take so if this is the grade, then you take the grade and divide by 100, and then take the square root, and then multiply by 100 again. Like I said, I don't know if you do this in Nigeria, but this is very common in the US. And this curve, the whole curve will shift up like this, and you have a much more reasonable distribution. So in some sense, when we use this S here, we are grading on the curve. Right. So now let's look at what this results tell us. In this case, we are plotting mean absolute error here and root mean squared error here. So lower is better because you want less error. Okay. So it's clear that this orange is better than the others. That's support vector regression, which is a fairly new technique. Okay. So if we compare across algorithms, it looks like the orange is consistently the best one, although this blue right here gives the overall best. Another thing we can notice is that going across, there is a general downward trend. This one is higher than this one, although from this point on, it seems there's very little improvement. So this is telling me that these predictors that do not include spatial information do not perform as well as these predictors that include spatial information. If I add the timestamp and the square root, it does not have much effect. Although if I look down at root mean squared error, it seems that the square root, this does what we would expect. It reduces the outliers. If I use the square root of the scale, I'm reducing the outliers. So you can see that these algorithms are performing, these predictors are performing better in the RMSE mean, in the RMSE measure, but not necessarily in the MAE measure, because the RMSE is picking up the reduced outliers. Another thing you will notice is that we've grouped the data, we've grouped the predictors in groups. These are predictors without spatial information. These are predictors with spatial. These are predictors with spatial and time. These are predictors with spatial, time, and square root. You can see the first in the group is doing the best. The first in the group, if you look at the chat window, you'll see the first in the group uses only the previous month and the previous month and the month 12 months previous. So if I add more information, I'm just confusing the algorithm and I'm making the performance worse. All right. So it's not true that more is better. It's not true that more data is better. You need to select your data carefully. All right. So overall best is just to use previous month and 12 months previous. All right. So this data does give you a story. It tells you many things. It tells you, first of all, support vector regression is better. It does tell you that the square root does influence the outliers. It also tells you that if you just use the previous month and 12 months previous, that's going to be your best predictor. All right, so that's what we can gather from this set of graphs here. And here you can see visually that the predictions obtained actually seem to do quite well. So here's your original image. Again, this is upside down South Africa. And you can see that the patterns of bright and dark are matched by the original image and the predicted image. The predicted image underpredicts the groundwater levels here. So it's always going to be more difficult to predict the outliers than the non-outliers. But this area with low groundwater is predicted well here. And you can see this shape here of low groundwater is very well predicted. So you do have some features that are very accurate. And here you can see this is bright, and then you have a bright spot here, a bright spot here. So you are getting some of the features very closely modeled. Okay. Now here's this is a very informative plot. What this shows is the measured pixel values versus predicted pixel values. So if I look at the previous slide, there are many, many pixels here. I think it's actually, it looks like 51 by 47 pixels. So each image has 51 by 47 pixels. And we put all of those pixels together. So I think, Eslam, you can tell me, I don't know if this is for a single image or for all the images. But what we did was for all the pixels in the image or group of images, you plot the measured pixel value. In this case, it goes up to about 110 is the maximum value. And we plot that versus the prediction from a particular prediction. All right, so this was from all images. Okay. So the prediction comes from one of the particular algorithms we had. So this is extreme gradient boosting plus Gaussian mixture model. So we use the Gaussian mixture feature I mentioned a few slides back. So of course you want your prediction to agree with your measurement. So if the measurements lie on this line, it's ideal. The closer the data point to this 45-degree line, the better. And if your prediction was perfect, then all the data would lie exactly on this line. Now we notice this square of values down here. This is just saying that most of the pixel values are very low. As we saw, most of the pixels are dark and not light, and there are just a few bright ones. So it's hard to see down here what's going on. But for the outliers, you can see definitely that the red pixels, the red data points are closer to the 45-degree line than the green ones. These green ones are way out, and they have shifted in. Now it's quite interesting that the measured, if you compare the red and the green, the red and green have the same measured values, but different predictions. So somehow these, I'm sorry, so let me be clear about the difference between red and green. Red and green are two different predictors. The green is the untrained. I think green was just previous month. Eslam can correct me if I'm wrong, but I think that green was using the previous month as a predictor of the pixels in this month. Okay, so yes, that's true. And the green was using this more complex predictor that was developed and trained. Okay. So you can see that for these outliers, for the untrained, there's some outliers that go way up here and some outliers that go way down here. In this case, the predictor is over-predicting the actual value. In this case, the predictor is under-predicting the actual value. So it would be interesting to look at the data and see which pixels are being over-predicted and which are under-predicted. So that would require more in-depth examination of the data, but it does seem that there's a very clear dichotomy between some types of pixels that are over-predicted and some that are under-predicted. And it seems that very few are predicted accurately for these outlier values. Now, what's happened with the XGB predictor is that it looks like these over-predict that some of these over-predictors have been moved down closer to the line. And certainly these under predictors have also been moving close to the 45-degree line. But somehow these over predictors have become under predictors, because these points up here must correspond to some, like this green point here must correspond to one of these red pixels down here. Okay, so these over predicted pixels are becoming under predicted. So that's interesting. We didn't look at this in detail, but that seems like a very interesting feature. All right, so this was for extreme gradient boosting. This one is for support vector regression, and you can see that the red predictor and the yellow predictor have very similar performance. In fact, it almost looks, you can see some very common features. You see this group of points here. This looks very close to this group of points here. This one is slightly above the 45-degree line. This one is slightly below, but it looks very similar. This filament out here, you can see something similar here. Okay, and then this here, you could almost think of this like a constellation. You can see the same thing over here. So it seems that extreme gradient boosting and support vector regression are in some sense picking out similar characteristics to make their predictions. But there's still quite a ways to go. You can see that there's quite a gap between these predicted, these are under predictions. For instance, this pixel here, the level predicted was 40, but the actual value was 80. Okay. So you're not going to get perfect results. Okay, I have a question there. What's the best method to handle outliers? Well, that's, if you can answer that question, I think you can win $1 million. That's very difficult question. Now, it did mention that one way to handle outliers is to try to use the square root, but it's always going to be difficult to predict outliers because there's less data to predict your outlier with, and also outliers usually happen because of some unpredictable or some unusual occurrence. So it's always going to be more difficult to predict outliers. But looking at this curve, looking at this data, it does seem like there should be a way to improve the predictor to move these predictions up closer to the 45-degree line. And that's really getting your hands dirty with the data. That's not using some general method. That's looking in and seeing where in your data these pixels are. And that's something that we didn't do. Here's another way to represent the errors in your predictor. Okay, this is actually a cumulative distribution function. So let me try to explain what's going on here. What's going on here? Okay, move down here. All right, so all right, let me move this down. Okay. So what does this actually mean? Here we have deviation, and here we have accuracy. It says percent, but actually it's proportion. This should be proportion. This is 100%. Okay. All right. So what this means is that the deviation is the error or absolute error. Okay. All right, now, so if I look at this 5 here, I have 3 different predictors. This green was the simple baseline. Let's look at the simple baseline. If I look at the simple baseline, I go up here, and here I see it goes up to something like 0.8. So this is 5. This is the 0.5, 0.8. What this means is that 80% of pixels have error less than 5. Okay. Okay. For the green one is the untrained, for the untrained. Now compare this to the SVR. For SVR, if you go up here at 5, you are up to, well, it's probably about 90. Maybe a little bit, maybe up to 88. 5, let's just say it might be 0.88. Okay, this means 88% have error less than 5. Okay, so you can see the curve higher is better. Because it means that on average your deviations are less. Okay. Ideally, you would have a curve, you would have an elbow curve that goes straight up like this. And that would be, if you had something like this, then that would be all the pixels had no error. Okay, so you want to be as close to this as possible. So this is a visual way to really show you which predictor is better. So you can see in this case, the red predictor is better. The red is slightly better than the yellow. Now, is this difference significant? It's not really very clear. It's not really very clear. Yeah, again, that's a question that I think it's not addressed in machine learning. And I think some theory needs to be developed to tell whether this really is a significant difference or if it's just happened on the particular data set that we used. Okay. All right, so that's all I have for the my presentation. Now, if I go back and look at the questions here, I see a question on neural network. So this is referring, I think, to what I talked about in. Let me go back to my slide that I talked about that. Here I was talking about short-term and short-range and long-range correlations. So here it says, what is the relation between long correlation and the nonlinear activation function in neural networks? And I would say that the correlation and the activation function are very different things. The activation function, when you get this result, you put this result through an activation function. But the activation function is not something that deals with correlations. It's a way of making your outputs more uniform. So I'd say there's really not much of a relation between the activation function and correlation. And here it says, how many types of nonlinear activation function do we have and which one is most efficient? There are many types of activation functions. I don't know how many, and I don't think anybody has a very good answer on which one is more efficient. I'm not really prepared to talk about when some activation function may be better than others. I haven't really prepared my talk on activation functions, so I would have to think about giving a better answer to that question. These all have to do with neural networks, which really is not the focus of my talk today. All right, well, let's look at the code. And how much time do I have? Okay, so all right, so that's about an hour. So we can look at the code here. So I have the code up in 2 versions. Where is my Jupyter? Okay, it should be here. All right, so here's the code in Jupyter. Let me just show you, well, if we talk about software, so we'll talk now about machine learning software. Now, there are many alternatives for machine learning software, but I think that Python is a very good option. You can also do machine learning in R, and there are other alternatives also, but Python is a very good option. you can download Anaconda, which is free. And what we're showing today is from Anaconda. Now, Anaconda has two user interfaces that are very useful for Python. One is called Jupyter. And one is called Spider. Now there are other interfaces for Python. There's something called PyCharm, and I don't know all the other ones, but these both come in Anaconda, and these are both very good. Now, Jupyter Notebook, I would say this is very good for getting started. Okay, it's very visual. You can see your code, and you write your code in small blocks, and you can arrange the blocks so they're easy to see. But Spider is for higher level development. If you're really doing serious coding, you should go to a Spider. So just to compare what they look like, Jupyter is here, and Spider is here. Spider has some similarity. The interface has some similarity to MATLAB. You have your code window. You have your console window. If I had some plots, the plots would appear in the window up here. So Spider is arranged to look something like MATLAB. So let me start with Jupyter and try to go through these statements so you can see what the code structure is. All right. So first you can see many statements called import. So this is obtaining packages needed for the processing. So in Python, it works this way. Python, if you want some particular function, you often need to import the package. And Anaconda already has many of these packages that are needed. Sometimes you may need to import additional packages. Okay, so this one is for image processing. This one is to also for data input. NumPy is the package that is used for numerical processing. Very key package that's used in most scientific processing in Python. I don't know what OS is. This is the plotting functions, and time is for timing your code. I mentioned that we use scikit-learn. So here we have we have several different functions within scikit-learn. Here's model selection. Sometimes a model will have parameters, and you want to optimize those parameters. So, for instance, support vector regression has parameters, and you want to find the best set of parameters for a particular model. You should do some kind of search. So, what grid search does is it does basically an exhaustive search through the possible parameters and finds the best model. Okay. This SVR, this is support vector regression. Okay, this one is linear regression, random forest regression. This is multilayer perceptron. Okay. Okay. And then here we have metrics. This would be the MAE and the RMSE metrics. Okay. Okay. And then this is XGB has a separate regressor that this package has to be obtained separately. Okay. So you can see in the chat window what OS is for. Okay. Let's see. All right. So first thing we need to do is obtain the images. The images are in this directory, and hopefully I have the right directory. So, so we create a list of files for the inputs and for the outputs. Now here, as you can see, we create the sequence of images. And what this does is well, let me show you the data here. The data is in a folder. And where's my folder? I think I can go here. Okay, I go to downloads, and I can find it down here, I believe. Should be down here. And then here we have this. And then I think it's this here. And if I show this in it's not going to show me. Oh, here we go. All right, let's try this. It's not easy to see, but these are all images. If I click on one, let me see if I can find one that has more brightness. Well, maybe this one. Now you can't see very well. Let's see if I can zoom in. Well, it's not completely black. There are some non-black pixels there. It's just hard to see. But these are all image files that have already been pre-processed. Right, so these are going to be the inputs to our algorithm. Right. So what this does, oh sorry, I'm still in Jupyter. So what this does is it reads the I think what it does is it all right. So this one is taking a so this takes the XPath array. These are the images that are going to be used to create the list of inputs. These are the same images that are also used for outputs. Here, first of all, you find the size of the image, and the image will be arranged into pixels. All right, so here we've got the right. So basically, this part here is opening this part is opening the images one by one and pulling out the pixels and putting them in a vector, and so that the input is arranged. Okay. All right, and that function is used to put the data set together. I'm not sure how much I want to do this in detail, but let's see. So here you see some different functions. Some of the pixels in the image are not used because they're over the ocean, so they have no groundwater. Okay. So these are removed from the list of pixels. In this case, you see that the square root function is used on the data. Here you add the pixel location and timestamp to the data. And then here's your returned data set. So in this case, we're using an array length of 12. Now, if you want to look at the different predictors, in this case, month ahead is going to specify which of the predictors A, B, C, D, E, F, G that you're going to use. In this case, we're just using the 12-month previous one. No, I'm sorry. 0 stands for one. I got this wrong. 0 stands for one month ahead. If I wanted to predict 2 months ahead, I could put a 2 here, or a 1 here. Or if I wanted to predict 3 months ahead, I could put a 2 here. But everything I talked about in my talk today was just for predicting the next month. Of course, if you want to predict too much in advance, the prediction is going to be less accurate. So features, these are the list of features that I used. In this case, I used the 12 months previous and the previous month. And here I specified the linear regression. Okay. So let's see. So let's see what's going on. So Eslam, can you say anything about this? I think this is just doing the processing. All right, here's where you call a making data set. So this is where you put the data set together. And then let's see what else we have. And then here's where you actually do the, you can do more than one estimator at a time. And it gives the, here it's going to give the results. And here you use the predictor. And here you can see that mean absolute error and root mean squared error. And the R squared score. If you know regression, you know there's an R squared score. So this gives all the scores. All right. So I think that's all I need to do. And I have the same thing in the Spider. So I think I'm going to go ahead and run it in Spider so you can see how that works. Well, I'll run it here and then I'll run it in Spider. To run this one, you can just go to, I don't even remember. It's Control Enter. I think it's Control Enter. Oh no, I'm sorry, because this is the .py file. This is not the Jupyter file. So I need to open I need to open my Jupyter notebook. So let me go back to that. Let me see if I can find this. Where is it? Here it is. Oh, I think it's here. I don't remember where it is. So let's just go to the Spider. Eslam, if you can tell me where the Jupyter notebook is, I'm not sure where I put it. Or if you can tell me what the name is, I can try to find it. All right, so Eslam said that this is just down here, we're calling the functions and split into training and testing. And so that's down here. All right, yes, here you go. So you can see here that we have you have the test images here, and then you have the training images here. So this minus means that the last 12 images are used for testing. And then this means all the rest are used for training. Right, so let me go ahead and run this in Spider. This is the same code here. It's just the interface looks different. You can see all the same things here. All right, so let's go ahead and run it. All right, so it's processing the data. And it should give me some output in just a moment. It's loading packages, so it takes longer the first time. All right, so here you can see the results. Mean average error, mean absolute error, mean squared error, root mean squared error. The root mean squared error, of course, is the square root of the mean squared error. and the R2 score, so about 0.5. So this is okay. Now this one uses only the 0 months ahead, and it uses features 0 and 11. Now, if I just used 0, you could see the change. If I use 0, I should have a prediction that's not as good. So let's look at this. Should be a little bit faster this time. All right. So you can see if you compare these two values, you see the mean absolute error is quite much bigger, and the root mean squared error is also much bigger. So if you compare these directly, you can see that using 0 and 11 is better than using just 0. Now, if I did something like 0, if I tried to use more, now my claim is that if I use all of this data, it's going to confuse the algorithm, and the performance will be worse than the original. My best performance so far is 2.857. So let's see what happens if I add more months to predict. This should be worse than 2.857. By the way, if you want the code, you can see that there's a place to download on GitHub. You can see that in the chat window. So if you'd like to use the code yourself, you can do that. I'm not sure how long this one will take. All right, so this one's 2.92. And if you remember for the mean absolute error, 2.92. And my original one here was 2.857. So it's not doing as well. Now here I have linear regression. This was not my best result before. Let's see what other options I have. It looks like I can use SVR. So I believe I can just do here, and then I believe I can just do SVR like this. All right, let's try XGB. Let's see if but I'm not sure I have XGB. I don't have XGB loaded. All right, let's see if I can uncomment this. I'm not sure if I have this. We can try it. We'll try that instead. And then here, let me go back to 0 and 11. Okay. Okay, so we'll try this one. I'll see if this works. I'm not sure if I have this regressor loaded. So we can try it. Let's see, is it done? No, it's not done yet. The red, okay, there we go. All right, now look at this. You have 2.3 for XGB. You compare that to for a linear regression, our best one was 2.8. Okay, so you see there's quite a bit of improvement there. I can compare this one to Random Forest. Let's do Random Forest. Random Forest would be here. here, put it here. Where was it? Okay. Oh, it's there. Okay. All right, so let's try this one. Okay, it's coming. A little bit slow. I don't have the fastest computer here. All right, well, while we're waiting, I think that's really all I have prepared today. And if people have some questions or we want to have some discussion, I guess now is the time to open up. We can, when the results come, we can discuss those. Well, let me give it back to the moderator. If there's anything you want to, we can open the floor for discussion. So please go ahead and if you have questions, go ahead, type in your chat window. Hello, Prof. Just came on. Nice to see you.
Thank you, Tron. You are welcome.
Yes.
Thanks for your wonderful lecture. We appreciate it.
I should probably also put my, if people want to discuss this further, I can put my email in the chat window, I suppose. So let me just do that.
I think that's better. If you have any question, please type it into the box so that Tron will be able to attend to you. You can see his email in the chat box. So you can type in your question, or if you want to ask directly, just raise up your hand. The host will unmute you.
We can, I know that many people are interested in neural networks. We can try to talk about those. I think many questions I won't know, but we have other experts here. If you want to ask about neural networks, we might be able to give you some answers.
Yes, I know people like Dr. Sawyer is here. Maybe it is his area. Also free to answer questions that comes up. So please type in your question.
All right, so someone said, someone asked about a Python class. There are some very, very good Python classes online. Someone sent me one and I don't remember the link. Let me see, I can try to look for it offline here. So I'm going to stop my share. I'll see if I can find in the next few minutes if I can find the link. But there's some excellent Python courses online, and I think that's where I would start. And they're free. Maybe some people may know of some Python classes and put that in the chat window. But these online courses, many of them you can do the coding in your browser, and the course will correct your coding.
Yes. Are you through, Tron?
Yeah, I'm through with my presentation. Yes.
What of the answer to the question on the material you want to recommend for Python?
Yeah, that's what I'm looking for right now.
Okay. unfortunately, we believe that by the time we do the next conference, that's the 8th conference, you will be around in person, and you will be able to teach that.
Yes, sure.
Much. Somebody has sent a link.
Okay.
I hope it will be suitable.
Yeah.
That's Dr. Abel Fattah. Thank you very much. Okay. Daniela Kimboru, can you ask your question?
Thank you very much, sir. Prof, please, when we fit our model and we are able to obtain our in-sample error, the one we call the sum of squares of error.
Yeah.
Now, is there a way we can track the out of sample error? Because we have for instance, after fitting our model, we can have a very small error. We'll be happy our model is doing well because of the small error. But what happened outside the sample? Maybe we pick a data set different from that. Is there a way we can use the in-sample error to track the out of sample error? That's my question, sir.
I'm trying to understand.
Okay.
I'm trying to understand exactly what you mean about
Okay.
in sample and out of sample.
Okay.
I'm not sure if that's related to what we call training and testing set.
Okay.
So I'm really not sure. I think I would have to talk to you more in detail about what your particular application is, because I'm not really sure how you're using that terminology.
Okay. This is what I mean. If I fit a model.
Can you give a specific example? All right, so you have a model.
Okay, for instance, the regression model.
Okay, yes.
I will obtain my sum of squares of error there.
Okay.
Then maybe the error is very, very small. And I'm very happy that this is a very good model. It's giving me a very small error.
Yes.
And I remember really that one of the problem of regression error, the downside is that when I'm fitting regression model within a range of data set, for instance, maybe 1 to 10, if I put 15 in the model might not behave well. Because I'm fitting the model using range of data from 1 to 10. I'm now picking a data, for instance, picking 20 just to test.
I see, okay.
Are you getting it, sir?
Yeah,
so
okay.
Now, so the 15 I'm putting to test the model now is not within the range of the data set.
Yes.
So are you getting the question now? So
yeah,
that implies that is there a way, having fit the model with that data set that I have with me, to track the out of sample error that I can think of? Is it possible?
Okay. Well, I'll tell you what I think. I hope I'm sharing my screen. And I believe the answer is no. And I'll show you why.
Okay.
Because suppose you have a case. There might be some physical system. Whoops, sorry. It really depends on the system you're modeling.
Okay.
Suppose you have a system here. So for this red, I'll use for the theoretical behavior. For instance, certain amplifiers have nonlinear behavior.
Okay.
And so they amplify like this, and then they flatten out like that. Okay. Now, suppose my data is all here. Right? If my data is all here, then I'm going to predict a linear, my linear regression is going to be this way.
Okay.
It's going to be here. Right? So if I take a data point out here, I'm going to predict here.
Yes.
But in fact, the actual behavior is down here.
Yes.
All right. Now, there is no way to tell from this information down here that the theoretical model actually has this curve behavior. There's no way to tell.
Okay.
So I think the answer to your question is no.
Okay.
And there's a mathematical reason why not. It's possible that you might have some amplifier that has this kind of behavior, Maybe it doesn't curve down, maybe it curves up. Maybe it curves up like this. There's no way to tell where it's going from this data down here.
Okay.
This is, I mean, this is the problem with extrapolation.
Exactly. Get that?
All right.
Yes, sir.
You cannot extrapolate unless you know something about your particular data.
Okay.
There's no mathematical way. Maybe if you have some other knowledge, you might be able to do it. But if you don't have extra knowledge, there's no way to do it.
Okay. But Prof, if I'm thinking like that, if I have my in sample error, if I want to track the deviation from the out of sample error, then if I now define a tolerance for myself that, okay, let me tolerate 5% tolerance, that if my out of sample deviate from the in sample with this small value, then is it possible that, okay, I have my in sample minus the out of sample, if it's greater, is less than this tolerance value, then I can collect the lifetimes of the in sample error I've obtained, then make the out of sample error subject to formula, then use my tolerance to manage that. Is that realistic, please?
All right. So if you, I'm still not sure I understand your question, but if I understand your question within the context of this picture, your in sample error would be computed from these values here. So these are all in sample errors.
Yes.
All right. Now, my out of sample error, so if I take several points out of sample, out here, my out of sample error is this.
Okay.
It's enormous errors. So what is your question?
That, for instance, if I'm not saying that I want to define that if my in sample error deviates from my out of sample error, if it's less than a very small value,
Okay.
then the small value I define it to be 5%, maybe my significant consideration, that tolerance value, maybe 5%. So
Okay.
since I know that value successfully, then I cannot think of, okay, let me collect this, make the out of sample error subject to formula, then I collect the lifetimes to that place. Then if I can add it, okay, I can say, oh, this would likely give me the out of sample error. The deviation means that I'm subtracting the in sample from the out of sample. Then if it's less than the tolerance, I'm using inequality now, a less than sign. Then if it's less than that value, then I will collect lifetimes, then I will have the value, I will assume. Then I'm not saying is that assumption reasonable? That will give me the possible out of sample error that I'm having.
So,
so that I'll be able to know how the model will behave out of, maybe I'm picking a data set that is not within the range of the training set.
All right, so what you're saying is that, in fact, you're saying that out here, so you have your model like this.
Yes, sir.
It's like this. And this was in sample, and then you have some out of sample. Here's your model here. So your predictions are here. Your prediction is here, and maybe the actual value is maybe the actual values are you said within 5%. So maybe the actual values are here. I should actually use another color for this. So your actual values are something like this, and so you're getting small errors out here.
Exactly.
So I guess you want to so I'm still not sure what you're trying to do. I mean, if you measure the out of sample error, you just say that's what the out of sample error is. Are you just trying to say that the model is valid out of sample?
Exactly. That's something else.
But I think, I don't know. I think that all you would do is you just report the out of sample error.
Okay.
And you say out of sample error is less than 5%. And that validates your model. Okay.
Okay.
I'm not sure if you can do anything more than that. I don't know what else you could conclude from that information.
Okay.
Are you trying to conclude something else?
Yes. For instance, if I featured the model,
yes,
the the sugar content added to that's the beverage type.
Okay.
The value where we collected it, it ranges from 1 to 10. So when someone asks that, okay, they recommended that I should take sugar more than 10 grams.
Okay.
So now we already have a model for the company that, okay, this model will work very well when the sugar content is from 1 to 10 grams. Now
Okay.
someone is now asking us that, oh, I need a beverage that will contain 15 grams. So now let me see how the model will perform if I put that 15 in the model. And I
Sure.
discovered the model just completely fall out of the old prediction.
Okay.
That was exactly what happened, sir. So if I now even put 30 grams, oh, the whole thing was in the old situation. So that was what actually made me to now try the radial basis function neural network model for that same problem. So I was now thinking then that, oh, is it possible I can track out of sample error using the in-sample error? That was what prompted the question, sir.
All right.
But I've not been able to get anything reasonable from my end there.
Well, as I said, I think I would have to stick with my original answer then in that case, because
All right, sir.
because certainly if you have results from 1 to 10 grams, going out
Yes,
to
sir.
30 grams is very, very dangerous.
Very, very dangerous.
If you think about drugs,
Exactly.
if you say, oh, I have a dose of 10 milligrams, and it's 50% effective. That doesn't mean if you go up to 100 milligrams, it's going to be 100% effective. You
Exactly.
might kill the person.
Yeah,
So,
exactly. Yes.
so especially with drugs, I think that kind of, and if you're doing extrapolation of 300%, that seems like it's very problematic. And I don't think that anything can help you. Radial basis function, neural network. I don't think anything can help you. That's like trying to read information from noise.
Okay. But what I observed from the radial basis function, I took the advantage of the negative exponential, because the negative exponential in the radial basis function will transform the data.
Dr. Kimboro.
Mr. Akimburu, sir, I'm not Dr. Yes, sir.
Don't worry, you go reach there. Eh?
All right, sir. Thank you, sir. All right, sir.
Not by faith is for you.
Amen,
Okay.
sir. Thank you, sir. All right, sir.
So now you will connect with him later.
Okay.
Okay,
Sure.
all right, sir.
And
Okay.
Tron will send his email address.
Yeah, I sent
Okay,
all.
sir.
Uh-huh.
Sent already, sir. All right, sir.
Well, in research like this, don't hesitate to collaborate if need be.
Okay.
Oh, yes, sir. Yes, sir.
If Tron that it can be of help and it will take him some time, you
Okay,
can
sir.
collaborate with him
All right, sir.
and jointly publish. Tron is
Okay,
always
sir.
available to assist.
These
Thank you very
are
much,
very
sir.
important questions because I think all too often people want the data to do too much. Data has definite limitations,
Yes.
and there are some and it's important to know what they are.
All right, sir. Well, thank you very much, sir.
So, Tron, can you send your email address?
Okay, sure.
Just send your email address to me.
Okay, sir.
I put in. Okay.
Yes, I've copied that already,
Okay.
sir.
Okay. Yes.
Okay.
All right, sir.
So finally, with the last question, please, if anybody has question, either you type it in to the chat box or you raise up before we call it a day.
I wasn't sharing my screen all this time, so I didn't show the picture. So here's the picture. I didn't realize. All right, never mind. So
I think, yeah. So, well, in the absence of any further question, one, we want to appreciate you again, Professor Tron, that you are about 6 hours behind. So, very early for you.
not 6 hours. I think it's
six hours. Okay.
8 hours.
So that means you.
It's almost 6. It's almost 6 a.m. I started my talk at 4 a.m.
Oh, 4 a.m. Oh, thank you very much. That's a big sacrifice. We really appreciate you.
Yeah. That's okay. I just
And we have benefited. Yeah, yeah. So we benefit a lot from your teaching. We appreciate that. Then all of us too that are listening, if there's a good teacher like Tron and there's nobody to listen, we will also not be satisfied. So we appreciate your joining us to benefit from this very good lecture. The last one will come up by 3 p.m. on modeling, and enjoy that one very much too. So we encourage you to join. So thank you very much. Strong friends online. I will send more information to you.